So we want to solve the boundary value problem for the heat equation. Here is the differential equation. We're on the x interval from 0 to 10 and for t greater than 0. So we're solving it forward in time. Now we have some boundary conditions. We know that the x derivatives of our heat function, we're demanding that they be equal to 0 for all time. All right, so here the boundary conditions have to do with the x derivative of our heat function, and the initial distribution of heat is given by, at time equals 0, is given by x squared, 10 minus x squared. So what we want to do is we want to use Fourier series to solve the heat equation forward in time. So let's remind ourselves how to do this. We remember that this all boils down to an eigenvalue problem. So we have to choose the eigenvalue problem that corresponds to the initial conditions, the boundary conditions that we have. And the boundary conditions have to do with the derivatives at the endpoints of our interval. So we're going to be using this eigenvalue problem with the derivatives set equal to 0. And we know that the result here is that the eigenvalues, this has eigenvalue 0 associated with the eigenfunction 1, and infinitely many other positive eigenvalues given by this, with associated eigenfunctions given by cosine. And that's all of the eigenvalues. So using those functions, we can write down our Fourier expansion and solve the heat equation. And so the heat equation, the solution, will be written in this form. The A0 is the projection of our function, of our initial function that we were given, onto the first eigenfunction. Right? And that is given by this formula right here. And the ANs, the subsequent ANs, are the projections of our initial function onto the associated eigenfunctions here, and that is given by this formula right here. So these are the things that we need to compute, and then this will be our answer. So let's compute this stuff on the left. So we need to compute the denominator. That's the integral from 0 to L of 1. Right? Well, we're on the interval 0 to 10, so this is just the integral from 0 to 10, and we know that's just equal to 10. Right? So done. That's 10. Now we have to integrate our function from 0 to 10. This is something we could do by hand because it's a polynomial. Let's just go ahead and use Wolfram Alpha, a computation engine, to do this a little more quickly. So I'm going to go here, and I'm going to integrate our function x squared 10 minus x squared from 0 to 10. All right, let's see what we get. Okay, so I'm getting 10,000 divided by 3. Now remember, we're dividing this whole thing by 10, so this will just be 1,000 divided by 3. And so that is our A0 term. And so we can immediately answer that part of the question. There we go. Now what about this stuff? Well, for that stuff, as we said, we have to compute the projection of our function onto the cosine terms. Well, the denominator is this cosine squared integral, so let's compute that out. So we're going to put cosine squared n pi x over 10, and we're going to integrate that from 0 to 10. Now, Wolfram Alpha assumes the variable will be x, so that's what we want, and that should be fine. And we can see it got an answer here. Now, it looks a little ugly, but if you look at it closely, it's not that bad, because sine of 2 pi n when n is an integer, that's always equal to 0, right? So this whole stuff over here is 0, so the answer is just 5. Okay, so our denominator is 5. What else do we need? We need to multiply f times the cosine function for the numerator. So let's go ahead and do that. So let's put our function, let's take the square off of cosine, put our function f back in here, multiply it. Now remember, we're dividing by the answer that we just got. So I'm going to multiply this by 1/5, just to get everything done in one fell swoop. So there we go. Let's give Wolfram Alpha some time to return an answer. It's still working. And there we are. Okay. So, okay, that looks pretty hideous, right? But again, it's not that bad because sine of pi n, when n is an integer, is always equal to 0. So that whole piece is gone. And then what else can we do? I can factor out a 6. 6 times 40,000 is 240,000. Let's write this down. So I have negative 240,000. And then I've got a pi n here and a pi n here. That's a common factor, so I can cancel that in the numerator and denominator. And that just leaves me with 1 plus this thing. And again, I'm canceling that stuff with what's in the denominator, so I lose a pi n down there. Right? Now, what's cosine of pi n? Well, that's equal to 1 when n is even, and it's equal to negative 1 when n is odd. That's the same thing as negative 1 to the n. So this whole thing just simplifies to this expression right here. And so those are our ANs when n is greater than or equal to 1. So this is the stuff that we need to put in to our solution here. So let's just copy that in here. And remember that this is all multiplied by cosine of n pi x over L, right? And then we multiply by e to the negative n squared pi squared divided by L squared t. Right? And so there we go. Now I want to point out one more thing here. If you make an observation, when n is even, this is just 1 plus 1, that's 2. All right, that just becomes 480,000. When n is odd, though, this is a negative 1. You add it to 1, you get 0. So we have no terms when n is odd. When n is odd, all of these are gone. So one thing you can do is you can just sum up just the even terms instead. So we can just change this to a 2, which makes this 48,000, right? Get rid of that stuff. And then just replace all the n's with 2 n's, because those are the only n's that survive. Only the only terms that survive are the ones that are even. So those are the form 2n. Right? So that's another way to write down the answer. Now I went ahead and graphed this so that we could see what was going on. We see that in the background here we have our initial function. That curve back there is the initial function. And then as we let time go forward, we can see that everything just kind of got, the heat just dissipated and became at one, kind of dissipated down to just one constant level. As the heat dissipates, it just evenly distributes itself throughout the interval. And so that's why it all flattens out.